Okay, so in the last lecture, we talked about the concept of underfitting and overfitting. And as a practical example, we were looking at polynomial regression. And there we have like y is approximately equal to beta 0, x0 plus beta 1, x1, all the way to beta d, xd. Sorry, and I actually meant to put these in the subscript. So we got x to the power 0, x to the power 1, x to the power d. And so here we can, in fact, we have to make a choice about what is d. How many terms do we include in our polynomial model? And we saw that if we choose d too small, then our model is not sophisticated enough to handle the real data, and that causes underfitting. But if we choose d too large, we have other problems where our model starts to fit the noise in the training data, and that's called overfitting. And what we discussed are ways to choose d by optimizing or by minimizing the sample MSE on some test data set through a procedure called cross-validation. And we discussed various forms of cross-validation, k-fold, simple test training splits, discussed the one standard error rule, all those different things we can use in practice. But this thing, polynomial regression, is just one example of this principle that occurs more generally in machine learning, that models that are too simple cause underfitting, models that are too complex cause overfitting, and we can choose our complexity of our model well by minimizing some metric. It might not be mean squared error, it might be something else, but through some metric through cross-validation. So generally speaking, the same procedures we talked about, but maybe instead of looking at mean squared error, you might look at something else. But we're going to continue focusing on mean squared error, but instead of the sample mean squared error that we were discussing, we are now going to start talking about statistical mean squared error. And we're going to show that quantity can be decomposed into three terms, what's called the bias, the variance, and the irreducible error. And we'll see that underfitting is when your model is too simple and your bias is large. Overfitting is where your model is too complex and your variance gets large. And essentially, we have this trade-off. When we choose model complexity, we want to balance between bias and variance, the bias-variance trade-off. And so that's a very fundamental idea in machine learning. And so today's a super important lecture with regards to machine learning topics. Okay, so that's sort of the roadmap. But the thing we need to discuss first is random variables. So this is one of the two main prerequisites of the course. We have linear algebra, and then we have some prior course in probability statistics, stuff like that. And so what I'm going to do is, over the next few slides, just review some of these basic concepts and establish a notation that we'll use in the class. And I did write something that is more formatted more like a textbook. That's a document. It's not very long. It might be like 10, 12 pages or something like that. So if you want to see all this material but with examples and more lengthy explanations, I recommend looking at this document, or of course, if you have books that you're familiar with on probability and expectation, you can look at those also. So let's just start at the very beginning. Until now, we have not really talked about any random quantities. We were just given a data set which is just like a list of numbers, and those numbers are fixed. They are what they are. But in machine learning, often we want to imagine what will happen when we apply our trained model on some data that we haven't seen, like the test data or the validation data. We might also want to say, like, what happens on average when I do this stuff in machine learning. And so that's what we want to do, describe what might happen or what tends to happen. And so for that, we need to turn to a set of mathematical tools called random variables. And a random variable is a quantity that, it's like a variable that can be many things. There's many different possibilities for that variable, and there's a probability of each one of those possibilities. So that's the idea. A nice simple analogy would be like if I have a bag of marbles, like a very big bag of marbles, and on every marble is painted with a number. And if I tell you about how I built my bag, like I might say, all the marbles in my bag are either painted 0 or 1, and half of them are painted 0 and half of them are painted 1. So now every time I draw out a marble, we don't know what that marble is going to be until I draw it out and look at it, but I know that with probability 1/2 it's going to be a 0 and probability 1/2 it's going to be a 1, right? And that bag of marbles describes that random variable. So that's kind of a nice analogy. Random variables are like bags of marbles. And so you sort of know how things will behave, on average or in variance or various statistics once you describe that bag of marbles. But you never know what any given marble will be until you draw it out and you look at it. Okay, so some notation then, or some nomenclature, is that the values of the marbles, once we actually have them, those are called realizations. And so, there's a random variable, but as soon as you know that that random variable took on the value 1, that's now a realization. That is fixed. Can't change it. And there's going to be two distinct types of random variables: discrete random variables and continuous. The discrete ones are a little bit easier to get a handle on. And just for the purpose of these few pages here, as well as this document, we are going to denote random variables using capital letters and deterministic or non-random variables using small letters. We can't do that for the whole course because we don't have enough variables to do that, but just for now, that's how we're going to do things to be as clear as possible. So here we have a random variable, capital A, and if this is a discrete random variable, it can take on values from a countable set, meaning like it could take values between 0 or 100, or it could take on any integer that is infinite but still countable, but it couldn't take on like all real numbers between 0 and 1. That is an uncountable set of things. There's no way I can make a list of that. So when this random variable takes on values from a countable set, we can make a list of all the possibilities that it can take on. And the way I'm denoting that is with these superscripts in parentheses. So this is the first of k possibilities of this random variable. This is the second, this is the third. So for example, maybe these are the integers 1, 2 through capital K. That might be what this discrete random variable manifests as. Or it might be like, 0, 2, 4, so on, even numbers. Okay, now these are the possibilities, and the probability that each of those possibilities occurs is given by this little p sub a. So this is random variable. It's saying the probability that this random variable takes on its first possibility, that's going to be a number somewhere between 0 and 1. And so on. And so we have a list. If we have k possibilities, then we have a list of k of these, the probability of each happening. And we can pack those into a k length vector. Now we have this bold-faced little p sub a. So that's the vector containing all the possibilities, and we refer to that as the probability mass function, or the PMF. And for these discrete random variables, once you know these two things, once you know the set of possibilities as well as how often they occur, you know everything about the random variable. There's nothing else to know. Okay, so again, this little probability, some real number between 0 and 1, this is how I'm going to denote it here. So this is the capital PR. You can just read as the probability of this event. And so here the event is that the random variable A takes on the deterministic value A sup K. That's what this means. And again, yeah, this is some real number between 0 and 1. Oh, and there's one other important property, is that the sum of these probabilities has to be exactly 1. The sum of the PMF has to have a total probability of 1. Okay, so that's discrete random variables. Any questions on those? Okay, now, as you can see, if I had an uncountably infinite number of random variables, I can no longer describe things this way because I can't even make a list of the possibilities. I can't, there's no way I can construct a finite dimensional vector or even countable infinite dimensional vector. So we have to do things a little bit differently with continuous random variables. That's where we have a uncountable number of values, and we'll assume that they come from the set of real numbers. So that's not going to include infinity or minus infinity, but anything else in between. And so for these, we describe them through their CDF, which is, we're going to denote it with a capital P sub A. And this is a function of a number little a, deterministic. And it's defined as, this is the probability that the random variable is less or equal to this small a. And so this is some sort of non-decreasing function. If you plotted it versus small a, it could be flat or increase. And eventually it goes up to 1, and you can't have a probability greater than 1, so it stays there. So this is one way we can completely describe a continuous random variable. However, for our purposes, we're more often gonna use the derivative of that CDF, which is called the PDF, or the density. And that density usually manifests inside an integral. Almost always it's going to be inside some integral. So for example, the way that the PDF and the CDF are connected is that the probability that the random variable is less than or equal to A can be described as the integral of that density. Here I'm using some dummy variable A prime because this is a fixed number, I can't use this. But notice that A occurs in the upper limit of the integral. So I'm integrating the density all the way from minus infinity up to and including A. And when I sort of integrate that density up to little a, that gives me this probability. That gives me that CDF evaluated at A. Okay, so I know you guys have seen this all before, but just to remind, yes?
Is that capital A a boldface A, or is it a variable?
Yeah, so right now this is just a scalar.
Okay.
Yeah, exactly. Good question. This is a scalar, so we will talk about random vectors, but for now, just to be simple, everything is scalar. Okay, so this density has two key properties. It must be non-negative. You can never have a negative density. And it must integrate to 1. If you integrate from minus infinity to infinity, it integrates to 1. So that's sort of the setup of the basic ingredients of these random variables. And there's a lot you can do with them. There's a lot you can learn about them. But we're really going to focus on just a couple things. We're going to focus on expectation and to a lesser extent variance. We're not going to get into a lot of more complicated things about probabilities or statistics, just the simplest stuff. So the expectation is just the statistical mean of a random variable. And to be a little bit more general, we'll talk about a function of that random variable. So this function might be like the squaring function or the absolute value or something like that. But the way we define this conditional this expectation, is this is going to be the integral from minus infinity to infinity of the function, and now I'm going to use the dummy variable of integration, and I'm going to use the density, and I'm going to integrate over A. Oh, sorry, this is, I meant to write that in the space below. That's for a continuous one. For the discrete one, instead of that integral, we have a sum over the capital K possibilities that the random variable can take on, and we know that those are A sup little k in this case. And then we're going to have the PMF, probability sub A comma little k. Okay, so these are basically this is the definition for discrete or continuous random variables of the expectation. So a simpler version of this is just the expectation of A. You forget about that function, and then you would just have like, A times its probability, or A times its density if you get rid of that function. But we often have a function there, like maybe you're looking at A squared, and so that means that this whole thing is like AK quantity squared, or this whole thing is like A squared. Okay. And all the properties of expectation, we'll go through some important ones. They can all be proven very simply just by looking at these equations and by doing simple algebra with these equations. But we won't even really dive into these two equations much. They're just sort of like, if you ever need to convince yourself of something maybe you forgot, you can always figure it out from these equations. But we're going to focus on these two key properties of expectation. So in stating these properties, we're going to assume we have deterministic functions, f and g, so these are not random things. And we have two different random variables, capital A, capital B. And let's first look at this. If I see the expectation, and also in this case, we have two deterministic, meaning non-random numbers, little c and little d. So if you see something like this, expected value of little c plus d times fa, we can use the linearity of expectation to basically say the expectation of this sum is the sum of the expectations. So the first term would be like expected value of little c. Second term would be expected value of df of a. But then second of all, because little c is not random, when you take the expectation of it, you just get c itself. A little bit how with those sample averages, if you had a quantity that didn't depend on the dummy variable of the average, that the averaging had no effect on it. You could just pull it out of the average. So here, what we have is this is going to be equal to little c plus, and then by linearity, we can pull d out of that expectation, and then what remains inside of it is just the stuff that depends on the random variable, which in this case is a. Now, we cannot pull this function out of the expectation unless it's linear, unless it's of this form c and d. So if f is a squaring function, you can't say that the expected value of a squared is the square of the expected value of a. Those are very different things. And I think that's all familiar from the deterministic case. So this statistical expectation, the intuition is it behaves very much like a sample average. So, it's just that instead of dealing with lists of numbers, we're dealing with these random variables, these marbles drawing out of a bag. Okay, so this is our first key property of expectation, which is we call the linearity property. Any questions on this property? Maybe I'll put this note. Note, expected value of fa is not equal in general to the function of the expected value of a. So we cannot simplify this further. Okay, Next thing we'll talk about is the independence property. So if you have two random variables, A and B, and you say that they're statistically independent, what that means is that they're joint density. So this is like a density, but it involves both random variables. That can be written as a product of the individual or marginal densities, probability of A times probability of B. Okay, so if this joint factors this way, then by using these, you can easily prove to yourself that this also factors into a product of expectations. So we get expectation of the function of A times another expectation of the other function G of the other variable B. Okay. But what's key is that it only works if they are independent. If A and B are statistically coupled in some way, you cannot split things like this. Okay, so this is just if they're independent, and so we call this the independence property. Any questions on that one? Okay, so these are the two main properties we will use over and over again in our class. So we won't even really get into this much, but it's there. It's important to know it just as an explanation of why this stuff holds true. Okay, so that's expectation. That's probably the most important thing, statistical average, statistical mean. Any questions on expectation? Okay, the second thing we will talk about is variance. And very similar to how it's defined in the sample case, the variance is the average of the squared deviation between the variable thing, the random A, and its mean squared. Okay, so if you replace this E with 1 over n times the sum I going to 1 to n, then conceptually it's identical to the sample variance. It's just instead of that list of numbers and that simple averaging of a list, we now have this statistical average. Okay, any questions on this? Now, if you remember, we saw that there was an alternate way to write variance when we talked about the sample variance. We wrote it first like this, but then we saw that it could actually be written as a difference of two terms. Does anybody remember how that worked? Basically, we can do the same thing here again. So let me ask someone, take a guess. It's okay if you don't know. Let me ask, is Adam Turpak here? Yeah, what do you think in terms of, if I want to write this variance in terms of one term that depends on A squared and one term that depends on expected A, quantity squared, how do you think we could do that? Thinking back to how we did it with the some type of averaging. Do you remember that? Okay, it's fine if you don't remember. But basically, we can look at the average value of A squared minus the squared value of the average of A. So this is another way to work with the variance, and this other way is often very convenient because this type of thing shows up in derivations. And it's a nice way to be able to relate it to the variance. Okay. So any other questions? All right. So moving on to a slightly more difficult topic is what's called conditional expectation. So conditional expectation is when you have two different random variables and you're looking at the average of some function of one given the state of the other. So let me give you an example. I might say, in Columbus, what's the probability that there's snow on the ground? And you might say, okay, if I think over the entire calendar year, snow on the ground probably 10% or less, something like that. You might say 10%. But then if I said, well, what's the probability that there's snow on the ground given that the temperature is 0 degrees? You would increase the probability that there's snow on the ground, right? So that's an example of conditioning. You have two random variables, which is snow on the ground, temperature, and they're related. And if I tell you the value of one, that influences the statistics of the other. And so that's basically the whole idea here. What is the average value of some function of A, given that some related random variable takes on the specific value little b? Right? So this might be the random variable of temperature in Columbus, and this is temperature is 0 degrees. So I'm asking like what is the something about the amount of snow on the ground, or just the presence of snow on the ground given the temperature. Okay, so again, this is the expectation of a function of random variable A given that some other random variable B, capital B, equals specific deterministic value little b. Okay, is that concept clear? It's a very important one because in machine learning, it's all about relationships between variables, right? Relationships between features and targets. It's that statistical relationship that is key. If they were independent, you could never do a prediction. So that's why conditional expectation, conditional statistics are so important in machine learning. Also many other fields. Communications is another one. Okay, so the way that this quantity is defined, written down mathematically, is it's very much like these, except rather than using this ordinary probability, we use the conditional probability. So I'll write it here. This is the version for the continuous random variables. So we have an integral, always goes from minus infinity to infinity, of the function of, in this case, some dummy variable A. And now I'm going to have what's called the conditional PDF. This is the PDF of A given B. And now we need to supply specific variables. This is working on that dummy variable A and given this particular value B. Okay. So if you look at this, once you perform this integration, there will be no little a left, right? That disappears once you evaluate the integral. But what will be left is somehow this value b. And so this whole thing is going to be a function of b. So again, like probability that there's snow on the ground, given that the temperature is 0 degrees or 10 degrees or 20 degrees, that thing will 0 versus 10 versus 20 changes that probability. Okay, so is this conditional expectation? Oh yeah, and then, okay, this conditional PDF is basically, it's the density of A given that random variable capital B takes on the value little b. It's just the density of A under that condition of little b. Okay, any questions so far? All right, so when doing this, we said that dummy variable A disappears. Similarly, when you evaluate this, the random variable A itself will also disappear. What comes out is some deterministic function of this value, this deterministic number b. Sometimes, however, instead of seeing this expression where b is fixed, you see this thing where you just leave out the equals little b. So in that case, everything works the same, except essentially that instead of the answer being fixed on b, the answer is now a function of the random b. So maybe as another example, we say that B temperature is either 0 or 80 degrees. And I can tell you how much snow is on the ground if it's 0. I can tell you how much snow is on the ground if it's 80, no snow. But now I might say, well, half the time it's 0, half the time it's 80. It's not true, but that would be maybe a grotesque model. And now, given those two conditions, you'd say, well, okay, now I have a random amount of snow on the ground. The snow on the ground is either going to be 1 foot or 0 feet. So it becomes random because I said that the temperature is one of these two things, but I can't tell you which one it is. It's random. So that's where we have this. It's very similar in spirit to conditional expectation, but rather than fixed conditioning, that conditional is still random. Okay, so this thing is still a random variable. Okay, now just how there were a couple of key properties for the basic expectation, there's just a couple key properties of conditional expectation. And if you memorize these properties, you don't really have to get into all those details that we described above. So here's the first one. And this is probably the most important one. So if you have some expression like this, expected value, some function of A times some function of B, and you are conditioning on A, what this means is when you take that expectation, you can pretty much pretend for the purposes of that expectation that A is deterministic. So what I mean is, if A really was deterministic by the linearity property, we know that we could just pull this out. And that's essentially what we can do here. So you would pull that out, FA in front, and then everything else remains. So you have G of B, and you still have the conditioning there. Okay, so this is the key idea when working with these expressions is whenever you see this, you can simplify it by pretending, for the purposes of this explanation, that A is deterministic. So in this case, you just pull it out by linearity. Okay, any questions on that idea? Okay, we'll do some practice of this today. There's an independence property that we can state too. So if you have something like an expression like expected value of some function of A given B, and these are independent, then basically that means that B has no effect on what we know about A, so we can just get rid of that conditioning. We can drop it. Expected value of the function of A. Okay, that's the main property. And there ends up being this sometimes very useful sort of corollary of this. If you somehow have to compute the variance of the sum of two random variables, and those random variables are independent, then you can split the variance into the sum of variances. Usually you cannot do this, but when they're independent, you can. Okay, so sometimes that makes derivations a lot easier. Okay, and then there's just one more property that shows up once in a while. So here we have expected value of some function of A given the value of another random variable. So we know that this inner expectation is a function of random variable B. But now, if we, in this outer expectation, remove the randomness from that B, we end up getting all the way back to expected value of the function of A alone, the law of total expectation. So let me give you an example of that. So if f of A is, again, the probability that there's snow on the ground, and this is the temperature, I could come up with some function that relates presence of snow to temperature. But now, in doing so, I'm treating temperature as random. Temperature could be, it has some density. Sometimes it's 10, sometimes it's 20, sometimes it's 30 degrees, and so on. So now I take that and I average over the temperature itself. Well, if I'm sort of, conditioning on temperature, but then averaging out the temperature, I get all the way back to what's the average probability that there's snow in Columbus. Okay, so there's a short proof of all these different things within this document. So if you feel like you need that these notes are too concise, because they're very concise, then you can go back and you can read things with explanations and examples and so on in that linked document. Okay, so that's it. That's our review of probability and random variables. That's all we need for this course. But again, we do need to be able to use this stuff pretty well, pretty fluently to get to the real machine learning concepts. So before we move on, are there any questions on any of this? And I realize this is very dense, and so it's probably something that either you know it already, or maybe you need to go back on your own time and go through these in a little bit slower pace. But that's really all we need in terms of probability and random variables. Okay, so now that we have this setup of how we work with these random variables, we're going to come back to machine learning, and we're going to present maybe the most important derivation for the whole semester. And basically, this is where we try to get a handle on the connection between statistics and underfitting and overfitting. And that involves defining this statistical mean squared error and decomposing it to bias and variance. So to even do that, we have to start at the beginning and say, what is our model? How are we setting up the basic model? So it goes like this. There's basically two models. There's the model that generates the data, called the true model, and then there's our prediction model. And generally speaking, these are very different things. So for the model that generates the true data, we actually have this occurs in two places. It occurs when we generate the training data. It also occurs when we generate the test data. And we're going to assume the test and training data are statistically matched. There's no mismatch between them. So the same model applies to training and test data. So here, I'm expressing it in terms of test data because I'm not using the subscripts I on things. But if I put the subscripts I on all these quantities, then you could think of those as the training quantities. Okay, so the true model says that the label is some function of the feature vector plus some random noise. So again, this noise is treated as a random variable. Now we're dropping the capital notation just because there's no such thing as capital epsilon and so on. So we don't have enough variables to really, for us, capital is still going to be matrices. Okay, so we have random noise, and we're going to assume, for the purposes of our derivation, that it's zero mean, and that the variance, we're just going to call the variance sigma squared, some finite number. Okay, so this is our random noise. You can think of this, on one hand, this is like the random noise in the test data, but at the same time, there's a version of this random noise in the training data as well. Okay, now we have a feature vector x. We are also going to treat this guy as random. Okay. Furthermore, the feature vector, this random quantity, is going to be statistically independent of the noise. So the features and the noise are independent. And this is very typical. Anytime in engineering, when you define noise, usually that noise is just independent of everything else. That's kind of what defines it as noise. Okay, so we have two random things, x and epsilon. And like I said, this applies to training and test. So training quantities would have i's on them, test quantities, no i's. And one more level of independence is that the training and the test are themselves independent with each other. So if you think, really we have a collection of n different training vectors, training vector x's and a test vector x, all those n plus one things are independent of each other. And they're also all independent of the n noise samples in the training as well as the single noise sample in the test quantity. So here we have, all these 2n plus 2 quantities are all mutually independent of each other. Okay, so this is the true model. Any questions on the true model? Yes.
So for the least square solution, we just predict y equal to fx, but why in this statistic model we will introduce a noise in the true model?
So yeah, so the true model, the reason why noise is part of the true model is that it reflects the fact that in practice, the exact data generation mechanism is almost never known. There's very, very few cases where you really know exactly how the data is generated, and if you do, that's like a almost trivial case. So there are cases where you very accurately know F, but epsilon is unknown. So for example, in digital communications, especially if you're like communicating in, certain environments, you just know you have Gaussian noise with zero mean and some variance. And that's really the only unknown. Everything else is known in the problem. And you can do a lot of like very deep theory in that problem because it's so clean and well described. But now if I start talking about like speech or language or images, like we don't even really know any good model for F. We assume that there exists one just for the purpose of like talking about it, but we never get to know it, right? Now in this unit, what we did is we focused on a nice simple polynomial problem, and we said that the F is a 3-degree polynomial with particular beta coefficients, right? But then we also added that Gaussian noise. And that gave us data which was, it's synthetic obviously, but it mimics a lot of real data. There's a trend, but then there's this noise in the training and the test that is just always there and can't really predict it. Now, but separately, let me continue answering your question. Separately, we have a prediction model. And so remember that in this unit, the prediction model does not know that the truth is third order. So the prediction model could be order 1, order 2, order 3, order 4, order 15, right? Secondly, the prediction model depends on some coefficients beta that we must learn. And so here, so F hat in this unit for the examples would be another polynomial model, but possibly of a different degree. But also, it's not going to contain the true beta coefficients. It's going to contain the coefficients that we learned from fitting using least squares on the test data. Now, because that data was modeled as random, and the coefficients are just a deterministic, least squares procedure on those, these coefficients are also going to be random. They inherit the randomness of the training data in this model. So when we finally look at the prediction model, we have two sources of randomness. X, the training features are random, and beta hat, the fitted or learned features from the training data are also random. We will assume that our F hat is deterministic, so it's just maybe like a 4th degree polynomial. That's it. And that gives us our prediction of this guy, y hat. Okay, so does that answer your questions? Okay, great. That's a great question, though. So we have the true model, and we have the prediction model. So beta hat, designed from the training data, which was random, and thus beta hat is also random. And now we're going to assume, kind of as before, because the training is independent of test, then this beta hat must be independent of the test features and the test error. Those things are all independent in this prediction model. Okay, so that is the prediction model. And now the way that these two things come together is they come together through the statistical mean squared error. So this is a new quantity we have not seen before, but is defined as follows. It's the statistical average of the square difference between the test label and the test prediction. But the way we're going to define it here is we're going to condition on the features, the test features. So this mean squared error will be a function of the test feature that we're using. Sometimes we also want to average or take another expectation over the x, in which case you get like an unconditional mean squared error. We'll talk about that too, but the way we basically set it up is this way. So just to contrast this with the sample MSE, MSE on the training, that would be, instead of the statistical average, we had the sample average. And then we had yi minus y hat I squared. So you can see that they are similar in spirit. They both have an average, but in one case you have a sample average, in the other case you have a statistical average. But otherwise it's just kind of the squared error. So these are not equal. This MSE, the statistical MSE is a new thing. Okay, so when you look at this, you might ask, okay, this expectation, this is averaging out some randomness of the argument. So what kind of randomness is in there? So let's look at y. So y has randomness due to x and due to epsilon, right? But because we're conditioning on x, for the purpose of this expectation, that means we're holding x fixed. So really for this expectation, x is deterministic because I'm conditioning on it. But I still have randomness due to epsilon. So this is random due to epsilon. And this guy over here, y hat, this is random due to beta hat. Because I'm conditioning on x, I'm treating it as deterministic. So this expectation averages over the epsilon from y and the beta hat in y hat, but it basically treats x as a fixed deterministic thing because of this conditioning. Okay. Yes?
How is beta hat independent from x if beta hat was designed based on x?
Because beta hat is from the training data, right? So beta hat is a function of this stuff, but this test stuff it has never seen when it was designed. That's how, yeah. Okay, great. So I think that's all we can do for today. So what we're going to do next time is we're going to do this sort of crazy looking derivation, but I'll convince you that it's not that crazy and you're capable of doing every step here. We'll get into that next time, but that is where we'll finally see this really important equation. And we'll get to practice some of our expectation identities and so on. But if there's no other questions now, then I'd like to just move on to briefly talking about the midterm. So the midterm did not go well at all. So here I have the grad histogram on the left and the undergrad histogram on the right. There are 25 total points, so if you scored perfectly, that would have been 25. No one scored 25. Some people got kind of close. But you can see that there are some people that are scoring almost 0. And that mean for the grads was just about 50%. Mean for undergrads, 9.52, was less than 50%. So this was not my goal in designing the test. I really was hoping that this would be just something that was kind of easy, that you guys, linear algebra is the prerequisite. You were told, this is important stuff. Got an exam coming up. Here's practice material. I was hoping that that would have been an incentive for people to really take it seriously and work on it and practice and get to know the stuff. And again, the reason why I'm trying to incentivize you is because this stuff is really important for us to get through the machine learning material. I didn't used to teach I didn't have that linear algebra lecture before a couple times ago, and I didn't have a test until the last time I taught this course and this time. But what I saw people encountering a lot of troubles like midway through the course where they would just tell me, I realize I have no idea what's going on because I don't know the linear algebra, so I just can't even understand what's in the lecture slides. And they're like, yeah, that's the most important thing for this course. Like if I could tell any future students, how do you do well in this course? You have to get the linear algebra down, otherwise you're in big trouble. And so that's my whole goal in having this exam, is just like to try to give you guys an incentive to learn this up front before it's too late, before you're busy with all the other things you do. So that didn't really work out the way I was hoping. There's a lot of people that it seems like, maybe you took the class a long time ago and forgot about it, but never really went back and reviewed it. So again, it is what it is, but the material is important. So I'm a little bit concerned for the people that are scoring very low here, whether they'll be able to really understand the machine learning once we get deeper into it, and where linear algebra is just kind of like how I describe things. I put up matrix vector equations and so on, describing the concepts. And if you don't understand what's the matrix vector, how do they interact and how do they work and what they mean, then it's kind of hard to understand the machine learning. So anyway, enough lecturing from me. So the solutions are posted. I think I had them come online at 5 p.m. The histograms are also on Carmen. You can look at these later if you like. And then I have your exams here, and I'm just going to call out your names one by one because this is the only opportunity I get to associate faces with names. So I apologize if I mispronounce your name in advance, but first we have Zhizheng Tan. Okay, please come up. Chris Gao. Cheryl Reddy. Cheryl here. Okay, what about Darren Ayrton? Carson Bryce. What about Zach? Nils Summerfield. Are you Zach?
Yeah.
Daniel Kowalski. Looks like Asia Chang. Jiachi Liu, L-I-U. Wes Waterstreet. Hannah Wang.
You, grandmother.
Thomas Wu. Ryan. Julio Rodriguez.
Oh, you are?
Eric Jackson.
I guess at that point.
Joshua Joseph. Eric Wang. Brandon Gemperline. Ellen Abdelnour. Yang Qian Guo, G-U-O. Alex Pater. Come on up. Frank Higgins. Alex Rizzotti. Sam Ben-Jerris. Charles Irons. William Clark. Yang Shen. Emily. Spencer Munch. Paul Gable. Luke Carter. Connor Sherman. Adam Turpak. question? GLA Leon? Last name G-E-N-C? Can't read that, sorry, can't read the first name. Beta Party? Justin Scupa? I named son? Daniel Singer? And Bert Green? Okay, does everybody have an exam? Okay, you guys are free to go. If you have any questions about grading, let me know. Yeah.
Yeah, because here we have to determine the beta and the F. So that means both are designed by us. So which one comes first? And how
So-
can we get that answer?
So right now we're just going to assume that like f prime is chosen and it's some function of some parameters beta prime, and then we train those on the data. And we're not going to directly ask the question of how to design them, but what we're going to do is we're going to decompose the mean squared error into three terms, and we'll understand that underfitting is sort of related to bias, that overfitting is related to variance.
Okay.
And then the way that we do it in practice is cross-validation and things like that. That's how we navigate this bias variance trade-off. And then we have like curves that show like as the model gets more complex, the bias goes down, but the variance goes up. So we want to be in the middle where we don't have high bias nor high variance. And that's gives us an understanding of how we do this choosing model complexity.
Okay.
Yeah, we'll get into all those details.
Yeah, thank you.
Sure. Hi.
I was just curious. On my exam, it says it's out of 20, and so I'm assuming does that just mean it's out of 25? And you just next.
Yeah.
Okay.
Sorry.
No, that's okay. I just want to make sure. Yeah. Okay.
Sorry for that.
No, it's okay. I just want to double check. Have a good weekend.
You too.
Thank you, Professor.
Yep. Have a good weekend.